butterfly flapping its wings may seem insignificant, almost meaningless. A movement so small that it disappears into the air without leaving a trace. Yet, in certain systems, that tiny motion can begin a chain of events that grows larger and larger over time. Not because the world is fragile, but because it is sensitive to how things begin. Chaos theory describes systems that follow clear physical laws yet remain deeply unpredictable. These systems are not random, they are deterministic, governed by precise rules. But even the smallest difference in their starting conditions can lead to outcomes that diverge dramatically. A fraction of a degree, a moment of delay, or a slight shift in direction can be enough to change everything that follows. Weather patterns are one of the clearest examples of this sensitivity. A small disturbance in the atmosphere can grow into a storm days later, making long-term prediction impossible. The same principle appears in nature, again and again, in the flow of rivers, in the rhythm of the heart, and in the complex activity of the human brain. This idea challenges a deep assumption we hold about the world. We often believe that with enough data and enough knowledge, the future should be predictable. Chaos theory suggests otherwise. It shows that uncertainty does not always come from disorder or chance, but from systems that are perfectly ordered and yet endlessly sensitive. As you listen, you may begin to sense how this applies beyond physics and mathematics, how small, unnoticed moments can quietly shape much larger outcomes, how the path of a life, like the path of a storm, may be influenced by details too subtle to ever fully measure. For a long time, science was built on a simple and comforting idea. If the laws governing a system were known, and if its current state could be measured precisely, then its future could be predicted. This belief shaped physics, astronomy, engineering, and even economics for centuries. The universe was imagined as a vast machine, moving forward with clock-like precision, where every effect had a clear cause and every outcome could, in principle, be calculated in advance. Uncertainty was seen not as a property of nature itself, but as a temporary limitation of human knowledge, something that would disappear as measurements improved and equations became more refined. This worldview began to fracture in the mid-20th century, not because the laws of physics failed, but because they worked too well. Scientists started to notice that certain systems followed their equations perfectly and yet produced behavior that could not be reliably predicted beyond a short time horizon. These systems were not random, noisy, or chaotic in the everyday sense of the word. They were governed by deterministic rules, often simple ones. And still, their long-term behavior seemed to escape every attempt at control or foresight, as if the system itself were amplifying uncertainty from within. One of the most striking realizations was that unpredictability did not require complexity in the equations themselves. Even systems described by a handful of variables could behave in ways that appeared irregular, erratic, and unstable over time. The problem was not the lack of order, but an excess of sensitivity. Tiny differences at the beginning, differences so small they could not be measured or even noticed, were being stretched and magnified as the system evolved. What began almost identically could end in entirely different states, not because of chance, but because of how the system responded to its own history. This marked a profound shift in how order was understood. Order was no longer synonymous with predictability. A system could be lawful, structured, and internally consistent, and still be impossible to forecast in practice. The future was not hidden behind randomness, but behind precision itself. The more finely the system responded to its initial conditions, the more fragile prediction became. In this sense, chaos did not mean disorder. It meant a kind of order that was too sensitive, too responsive, to ever fully stabilize into certainty. As this idea developed, it forced scientists to confront an uncomfortable truth. Perfect knowledge of the laws was not enough. Perfect measurements were not enough. Even infinitesimal uncertainty, unavoidable in any real observation, could grow until it dominated the system's behavior. This growth was not gradual or linear. It was exponential, unfolding quietly at first, then rapidly accelerating beyond control. Prediction did not fail suddenly. It eroded slowly, until one day it simply stopped being meaningful. Chaos theory emerged from this realization, not as a rejection of classical science, but as its extension. It accepted determinism while abandoning predictability. It showed that the future could be fully determined and still unknowable, that equations could be exact and outcomes still uncertain. This paradox lay at the heart of chaos theory and redefined what it meant to understand a system. Understanding was no longer about knowing what would happen, but about knowing why prediction would eventually fail. In this new framework, the universe appeared less like a clock and more like a living process, continuously responding to itself in subtle and irreversible ways. Small differences mattered not because the world was unstable, but because it was deeply connected. Every moment carried the memory of what came before it, and every step forward carried the imprint of tiny details from the past. Chaos theory did not remove order from nature. It revealed an order so intricate, so sensitive, that it could never be fully held in the mind. The turning point came when scientists began to realize that error itself was not merely a technical inconvenience, but a fundamental feature of prediction. No measurement, no matter how advanced, could ever be perfectly exact. There would always be a margin of uncertainty, a decimal that could not be pinned down, a fluctuation too small to register. For centuries, this had not been a serious problem, because most systems dampened those errors over time. Small inaccuracies stayed small. But in certain systems, researchers discovered something unsettling. Errors did not fade. They grew. At first, this growth was almost invisible. Two simulations, started with nearly identical values, would remain close for a while. Their trajectories would overlap, reinforcing the illusion that prediction was still intact. But slowly, quietly, the paths would begin to drift apart. A slight deviation would widen, then widen again, until the two outcomes no longer resembled each other at all. What made this so disturbing was that nothing external had interfered. The system had not been disturbed. It had simply evolved according to its own rules. This behavior revealed a hidden property of certain deterministic systems: extreme sensitivity to initial conditions. In such systems, the future was not shaped by large forces alone, but by the accumulation of microscopic differences. A change too small to measure could eventually outweigh every other factor. Prediction became less about understanding the system and more about an impossible demand for infinite precision. To predict perfectly, one would need to know the initial state with infinite accuracy, something that nature itself does not allow. This realization forced a re-evaluation of what it meant to model reality. Mathematical models had always been simplifications, idealized versions of the world designed to capture essential behavior. But chaos showed that even perfect models could fail in practice, not because they were wrong, but because they were too sensitive. The equations were correct, the logic was sound, and yet the future they described slipped away as time progressed, dissolving into a range of possibilities instead of a single outcome. What emerged was a new kind of uncertainty, one that did not come from randomness or noise, but from determinism itself. The system was not choosing between futures at random, it was following a single path dictated by its starting point. The problem was that this starting point could never be known with sufficient accuracy to track that path indefinitely. In this sense, chaos was not about chance. It was about the limits of knowledge embedded directly into the structure of reality. As scientists grappled with this idea, it became clear that prediction had a natural horizon. Beyond a certain point, forecasts lost meaning, not gradually, but decisively. The system still had a future, but that future could no longer be specified in detail. Only ranges, patterns, and probabilities remained accessible. Long-term certainty gave way to short-term reliability, followed by long-term ambiguity. The future was not erased, but blurred. This shift carried profound implications. It suggested that the universe could be governed by strict laws and still resist full comprehension, that knowing the rules was not the same as knowing the outcome. Chaos theory emerged from this tension, offering a language to describe systems where determinism and unpredictability coexist. It did not deny order. It revealed an order that unfolds with such sensitivity that certainty itself becomes unstable, slipping quietly out of reach as time moves forward. At first glance, determinism appears comforting. It suggests that every event has a cause, that nothing happens without reason, and that the universe unfolds according to fixed laws. For centuries, this idea implied predictability, the belief that if we understood those laws well enough, the future would become transparent. Chaos theory quietly dismantled this assumption by showing that determinism does not guarantee foresight. A system can be fully determined at every moment and still resist long-term prediction, not because it is unstable, but because it reacts too strongly to the smallest details of its past. In chaotic systems, the future is not shaped by a single dominant factor, but by the continuous interaction of countless subtle influences. Each moment carries forward the imprint of microscopic variations that accumulate over time. These variations are not errors in the system, they are part of its natural evolution. As time progresses, their influence grows, eventually overpowering any attempt to trace a single, reliable trajectory into the future. Prediction fails not abruptly, but through a gradual loss of resolution, until the future becomes indistinct. This creates a paradox at the heart of chaos theory. The laws are exact, yet their outcomes cannot be followed indefinitely. The equations do not break down, and the system does not become random. Instead, the link between present and future becomes too sensitive to maintain. To predict the system's behavior perfectly, one would need complete and infinite knowledge of its initial state, down to the smallest possible scale. Such knowledge is not merely impractical, it is fundamentally unattainable. As a result, certainty transforms into probability. Instead of precise forecasts, scientists are left with patterns, ranges, and statistical tendencies. They can describe what kinds of behavior are possible, and even likely, without being able to say exactly which one will occur. This does not weaken scientific understanding, it reshapes it. The goal shifts from controlling the future to characterizing its structure, from prediction to comprehension. In this way, chaos theory does not undermine determinism. It refines it. It shows that the universe can be lawful without being predictable, ordered without being transparent. The future still exists, shaped moment by the present, but it remains partially hidden, not behind randomness, but behind the delicate and unforgiving sensitivity of deterministic processes unfolding over time. Chaos theory ultimately forced a redefinition of order itself. For centuries, order had been associated with regularity, repetition, and predictability. A system was considered orderly if it behaved in a stable and foreseeable way, producing outcomes that could be anticipated far into the future. Anything that resisted long-term prediction was often labeled disordered, noisy, or chaotic in the everyday sense. Chaos theory challenged this classification by revealing that unpredictability does not arise from the absence of order, but from a different and more subtle kind of order operating beneath the surface. In chaotic systems, structure is present, but it does not reveal itself through repetition or simplicity. Instead, it emerges through patterns that never repeat exactly, yet remain constrained within clear boundaries. The system does not wander aimlessly. It follows rules, traces, shapes, and occupies specific regions of behavior. Over time, these patterns form intricate structures, not fixed paths but evolving landscapes that define what the system can and cannot do. Order, in this sense, becomes dynamic rather than static, something that unfolds rather than settles. This new understanding required a shift in how scientists interpreted complexity. Complexity was no longer a sign of randomness, nor was simplicity a guarantee of predictability. A system with only a few variables could generate behavior rich enough to rival the most complicated machines. The richness came not from the number of components, but from how sensitively those components interacted over time. Each interaction carried forward the memory of the past, embedding history into the present and shaping the future in ways that could never be fully unraveled. As this perspective spread, it became clear that chaos theory was not limited to abstract mathematics or theoretical physics. It offered a framework for understanding real systems that had always defied intuition. Weather patterns, ecosystems, biological rhythms, and even social dynamics began to appear in a new light. Their unpredictability was no longer seen as a failure of science, but as a reflection of their deep interconnectedness. Small influences mattered because the systems themselves were built to amplify them. Order, then, was no longer something imposed from above through rigid control. It was something that emerged from within, arising naturally from the interaction of simple rules applied repeatedly over time. This kind of order did not produce certainty. It produced coherence without predictability, stability without stasis. The system remained bounded, recognizable, and lawful, even as its exact future remained unknowable. By redefining order in this way, chaos theory softened the boundary between the known and the unknown. It suggested that uncertainty was not an enemy to be eliminated, but a feature to be understood. The goal of science shifted once again, away from the illusion of total foresight and toward a deeper appreciation of how patterns arise, persist, and transform. In doing so, chaos theory revealed a universe that is not broken by unpredictability, but enriched by it. In the end, this new meaning of order invites a quieter, more patient form of understanding, one that accepts limits without surrendering insight and embraces sensitivity as a source of complexity rather than confusion. The world remains governed by laws, but those laws no longer promise certainty. They promise something more subtle, a structure that can be studied, a behavior that can be explored, and a future that unfolds with endless variation within an underlying and invisible order. The idea that a tiny cause could produce an enormous consequence did not emerge as a metaphor, but as a disturbing scientific discovery. It arose from a simple question: why do some systems resist long-term prediction even when their governing laws are fully known? As researchers explored this question, they began to notice a recurring pattern. When a system was highly sensitive to its starting conditions, even the smallest deviation at the beginning could lead to outcomes that diverged dramatically over time. What seemed negligible in the present could become decisive in the future. This realization was unsettling because it challenged a deeply ingrained intuition about cause and effect. In everyday thinking, we tend to associate large effects with large causes and small effects with small causes. The butterfly effect inverted this expectation. It suggested that scale is not preserved as systems evolve. A minor fluctuation, insignificant in isolation, could be amplified through repeated interactions until it reshaped the entire system. The system did not require an external shock. It transformed itself from within, quietly magnifying its own internal differences. What made this phenomenon especially profound was that it did not rely on randomness. The system did not roll dice or choose outcomes arbitrarily. Every step followed deterministic rules. The amplification occurred because the system continuously fed its present state back into its future evolution. Each moment depended on the exact configuration of the moment before it. As a result, tiny discrepancies were not smoothed out. They were remembered, reinforced, and carried forward, growing in influence with each iteration. Over time, this sensitivity revealed a new way of thinking about causality. Causes could no longer be evaluated solely by their size or intensity. Timing, context, and position within the system became just as important. A small disturbance introduced at the wrong moment could have no effect at all, while the same disturbance introduced slightly earlier or later could alter the entire trajectory. The butterfly effect was not a guarantee that small causes would always produce large effects. It was a warning that under the right conditions, they could. As scientists reflected on this, they began to see the limits of human intuition more clearly. The mind is comfortable with linear relationships, where changes scale proportionally and outcomes grow predictably. Chaotic systems do not behave this way. They stretch and fold differences over time, transforming simple variations into complex outcomes. What begins as a barely measurable change becomes woven into the fabric of the system's evolution, inseparable from everything that follows. This understanding reframed unpredictability as an emergent property rather than a failure of knowledge. The future was not hidden because it was random, but because it was too dependent on details that could never be fully captured. The butterfly effect did not suggest that the world was unstable or fragile. It suggested that it was exquisitely responsive, shaped by a dense web of interactions where no detail was ever truly erased. In this sense, the butterfly effect marked a turning point in how science understood influence and consequence. It revealed that the future is not only shaped by powerful forces and dramatic events, but also by subtle shifts that pass unnoticed in the moment they occur. The world moves forward carrying the imprint of countless tiny beginnings, each one capable, under the right conditions, of reshaping everything that comes after. Sensitivity to initial conditions refers to a property of certain systems in which extremely small differences at the starting point grow larger and larger as time passes. At the moment they appear, these differences are so minor that they seem irrelevant, often falling below the threshold of measurement or perception. Yet the system does not discard them. It carries them forward, embedding them into every subsequent state. Over time, these microscopic variations are stretched, reinforced, and multiplied until they dominate the system's behavior. What once seemed insignificant becomes decisive, not through sudden change, but through relentless accumulation. What makes this phenomenon so unsettling is that it undermines the idea of a single, stable future. Two systems can begin almost identically, sharing the same laws, the same structure, and nearly the same initial values. For a while, their evolution appears synchronized, reinforcing the illusion that their futures will remain aligned. But beneath this surface similarity, divergence is already taking root. Each tiny discrepancy alters the next step, and each altered step introduces further divergence. Eventually, the two paths separate so completely that they no longer resemble each other, despite having originated from nearly the same beginning. This sensitivity exposes a fundamental limitation in prediction. To forecast the future of such a system accurately, one would need to know its initial conditions with infinite precision, not approximate values, not rounded measurements, but exact states down to the smallest conceivable scale. This requirement is not merely impractical, it is impossible. Nature itself does not permit infinite precision, and observation always introduces uncertainty. As a result, prediction is condemned to fail, not because the system is chaotic in the everyday sense, but because it is too precise in how it responds to its own past. The implications of this extend far beyond mathematics. Sensitivity to initial conditions means that the future is shaped not only by dominant forces, but by subtle contextual details that cannot be isolated or controlled. A slight delay, a marginal fluctuation, or an unnoticed variation can redirect the system's evolution entirely. The system does not average these details away, it remembers them. Each moment becomes a record of everything that came before it, and that record influences everything that follows, creating a future that is both lawful and irreversibly uncertain. This property also explains why long-term forecasts collapse, even when short-term predictions remain accurate. Early on, uncertainty grows slowly, allowing forecasts to appear reliable. But sensitivity ensures that this uncertainty grows exponentially, not linearly. There comes a point where prediction loses resolution altogether, where the future no longer exists as a single outcome, but as a spectrum of possibilities. Beyond this horizon, asking for precise forecasts becomes meaningless, not because the system lacks structure, but because its structure amplifies uncertainty too efficiently. In this way, Sensitivity to initial conditions reveals a deeper truth about complex systems. They do not erase the past, they amplify it. Every moment carries forward the imprint of countless tiny beginnings, woven together into an evolving pattern that cannot be untangled after the fact. The future remains determined, yet unreachable in detail, shaped by initial conditions so delicate that they vanish the instant one tries to grasp them. The discovery that would later become known as the butterfly effect did not begin as a grand theory, but as a quiet and almost accidental observation. In the early 1960s, meteorologist Edward Lorenz was working with a simple computer model designed to simulate atmospheric behavior. The model was governed by deterministic equations and was intended to improve weather prediction. At the time, computers were slow, memory was limited, and simulations required careful management. Lorenz believed that by restarting a simulation from a previous state, he could save time without changing the outcome in any meaningful way. One day, instead of re-entering the original data with full precision, Lorenz rounded the numbers slightly, entering values with fewer decimal places. The difference was minuscule, far beyond what any meteorologist would consider significant. At first, the simulation behaved exactly as expected. The numbers tracked closely, reinforcing the assumption that such a small change could not matter. But as time passed, the results began to diverge, slowly at first, then dramatically, until the new simulation bore no resemblance to the original one at all. This divergence was not caused by a flaw in the equations or an error in the computer. The system was functioning exactly as designed. The only difference was the initial input, altered by a fraction so small it seemed meaningless. Yet that fraction had been amplified through the system's internal dynamics, reshaping the entire outcome. Lorenz realized that the atmosphere itself might behave in the same way, following precise physical laws while remaining fundamentally unpredictable beyond a short time frame. The implications of this realization were profound. It meant that long-term weather prediction was not merely difficult due to insufficient data or computational power, it was limited in principle. Even with perfect equations, the atmosphere's sensitivity to initial conditions would eventually overwhelm any forecast. Tiny uncertainties in measurement, unavoidable in any real observation, would grow until they dominated the system's behavior. The future of the weather was determined, but it could never be traced indefinitely. As Lorenz reflected on this behavior, he understood that he had uncovered something far more general than a problem in meteorology. The same mathematical structure could apply to many different systems, from fluid dynamics to population models and beyond. What mattered was not the specific context, but the presence of non-linear interactions that fed small differences back into the system repeatedly. The system was not unstable. It was responsive in a way that defied intuition. When Lorenz later described this phenomenon using the now famous metaphor of a butterfly's wings influencing distant weather patterns, he was not suggesting literal causation. He was illustrating sensitivity. The metaphor captured the unsettling idea that no detail was truly insignificant, and that the future could hinge on differences too small to ever be fully known. With this insight, chaos theory moved from abstraction to revelation, reshaping how science understood prediction, control, and the fragile boundary between certainty and uncertainty. The image of a butterfly flapping its wings has become so widely repeated that it is often misunderstood. It is tempting to imagine a direct chain of cause and effect, where a tiny action triggers a specific distant outcome. But the butterfly effect was never meant to describe literal causation. A butterfly does not cause a storm in any simple or traceable way. The metaphor exists to illustrate sensitivity, not control. It points to how systems evolve, not to how individual events command the future. In chaotic systems, the butterfly does not act as a dominant force. It does not inject energy or direction into the system in a meaningful way. Instead, it represents the presence of an almost immeasurable difference at the beginning of a process. That difference could come from anywhere, not just from a wing beat. A thermal fluctuation, a rounding error, a momentary shift in timing. The specific source does not matter. What matters is that the system is built to amplify differences regardless of where they originate. This distinction is crucial because misunderstanding the metaphor can lead to the illusion that small actions always have dramatic consequences. In reality, most small disturbances disappear without leaving any trace. Chaotic systems are not unstable in the sense of being fragile. They are constrained, structured, and bounded. The butterfly effect does not mean that anything can happen at any time. It means that under specific conditions, differences that would normally be ignored can become embedded and magnified as the system evolves. The metaphor also does not imply that the future is manipulable through minor interventions. One cannot steer a chaotic system reliably by introducing tiny changes and hoping for a desired outcome. The same sensitivity that amplifies differences also makes outcomes uncontrollable. A small intervention could lead to many possible futures, not a chosen one. This is why chaos theory does not offer a method of control, but a warning about its limits. By framing the idea as a butterfly, the concept becomes intuitive, but intuition can be misleading. The true lesson is not about power, but about humility. It reminds us that prediction fails not because systems are careless or broken, but because they respond too faithfully to their own complexity. The future is shaped by details that cannot be isolated, measured, or repeated, making foresight increasingly fragile as time moves forward. In this way, the butterfly effect serves as a doorway rather than an explanation. It invites deeper inquiry into how systems remember their beginnings and how those memories shape their evolution. The metaphor dissolves once its purpose is served, leaving behind a more unsettling insight that the future does not hinge on dramatic causes, but on a quiet accumulation of differences that no observer can ever fully track or control. A deterministic system is one in which the future state is fully determined by the present state according to fixed rules. Nothing is left to chance, and no randomness is required for the system to evolve. At every moment, there is only one possible next step. This definition appears to promise certainty, suggesting that if the present is known, the future must follow transparently. Yet chaos theory revealed that this promise is misleading. Determinism describes how a system moves forward, not how well that movement can be tracked over time. The loss of predictability begins with the way information is carried through the system. In deterministic but chaotic systems, each moment depends with extreme sensitivity on the precise configuration of the moment before it. Tiny differences are not averaged out or dampened. They are preserved, stretched, and folded back into the system's evolution. Over time, these differences grow until they dominate the system's behavior. The future does not break away from the present. it becomes too finely dependent on details that cannot be fully known. This means that predictability does not collapse because the system becomes disordered, but because it becomes too exact. The rules are followed perfectly, yet they respond to initial conditions with such precision that uncertainty grows faster than knowledge can contain it. Even the smallest error in measurement, unavoidable in any real observation, becomes magnified through repeated interactions. The system remains lawful at every step, while prediction steadily erodes with each passing moment. As time progresses, this erosion follows a clear pattern. Short-term forecasts remain reliable, giving the impression that the system is under control. But beneath this apparent stability, uncertainty is expanding. Eventually, the uncertainty reaches a scale where distinct futures overlap, and the idea of a single predictable outcome loses meaning. Beyond this point, the future still exists, but it can no longer be described as a precise trajectory. It becomes a space of possible behaviors rather than a single path. This behavior challenges a deeply rooted assumption in scientific thinking that knowing the rules is equivalent to knowing the outcome. Chaos theory separates these two ideas. It shows that laws describe how systems evolve, but not necessarily where they will end up. Determinism guarantees consistency, not clarity. The future unfolds according to rules that are strict, yet unforgiving in their sensitivity to the past. In this light, unpredictability is not a flaw in understanding, but a structural feature of certain systems. It emerges not from ignorance or noise, but from the very mechanisms that ensure order. Deterministic systems lose predictability because they remember too much, responding to their own history with a fidelity that makes long-term foresight impossible. The system does not forget, and because it does not forget, the future slips beyond precise reach. At the core of chaotic behavior lies nonlinearity, a property that quietly reshapes how causes and effects relate to one another. In linear systems, change is proportional. A small input produces a small output, and doubling a cause roughly doubles its effect. These systems align well with human intuition, allowing us to extrapolate, estimate, and predict with confidence. Nonlinear systems break this comfort. In them, small changes do not scale predictably, and large outcomes do not require large inputs. The relationship between cause and effect bends, twists, and reshapes itself over time. Nonlinearity becomes especially powerful when combined with feedback. Feedback occurs when a system's output is fed back into its input, allowing the system to influence its own future behavior. This creates a loop, where each step depends not only on external conditions, but on the system's previous state. In chaotic systems, this feedback is not stabilizing. It does not smooth out variations. Instead, it reintroduces them, allowing even the smallest differences to be recycled and amplified with each iteration. The system becomes self-referential, constantly responding to its own past. As these feedback loops repeat, the system begins to stretch and fold information in complex ways. Differences that were once microscopic are pulled apart, spread across the system, and then folded back into new configurations. This process does not destroy structure, it creates it. Patterns emerge, not as fixed repetitions, but as evolving forms that never settle into a stable path. The system's behavior becomes rich and intricate, shaped by layers of interaction that build upon one another over time. What makes this especially important is that nonlinearity prevents simple averaging. In many systems, small fluctuations cancel each other out, leaving behind a stable trend. In nonlinear systems, fluctuations interact. They collide, reinforce, and distort one another. A minor variation introduced early can influence how later variations behave, altering the system's entire trajectory. The past is not overwritten. It is continuously active, shaping how new information is absorbed and transformed. This dynamic explains why chaotic systems resist simplification. One cannot isolate a single cause and trace its effect in a straightforward way. Causes overlap, interact, and merge, creating outcomes that cannot be decomposed into independent parts. The system behaves as a whole, not as a sum of components. Each element matters not in isolation, but through its interaction with everything else. Understanding becomes less about tracing lines of causation and more about grasping the structure of interaction itself. Through nonlinearity and feedback, deterministic systems gain their unpredictability without losing their order. The rules remain fixed, but their repeated application generates complexity that exceeds intuitive prediction. The system is not unstable or erratic. It is responsive, sensitive, and deeply interconnected. In this responsiveness lies the reason deterministic systems lose predictability. They listen too closely to themselves, allowing every whisper of the past to echo endlessly into the future. At first, it seems reasonable to believe that unpredictability could be overcome with better instruments and more detailed data. If uncertainty grows from small errors, then reducing those errors should restore control. This assumption has driven scientific progress for centuries, motivating ever more precise measurements and increasingly sophisticated tools. Yet chaotic systems expose a fundamental flaw in this logic. Precision does not eliminate uncertainty, it merely postpones its consequences. No matter how advanced the measurement, it can never be exact enough to halt the amplification of uncertainty over time. Every measurement, without exception, contains error. This error may be unimaginably small, buried deep in decimal places far beyond practical concern, but it is always present. In linear systems, such errors remain contained, shrinking in significance as the system evolves. In chaotic systems, the opposite occurs. The system treats these errors not as noise to be ignored, but as information to be preserved and amplified. Each iteration carries the error forward, reshaping the system's future with growing influence. This creates a situation where increasing precision yields diminishing returns. Measuring a system twice as accurately does not double the time over which prediction remains reliable. It may extend it slightly, but the exponential growth of uncertainty quickly overwhelms even the finest improvements. There is always a horizon beyond which prediction collapses, and that horizon cannot be pushed indefinitely outward. It is built into the structure of the system itself, independent of human skill or technological power. The problem deepens when one considers that measurement is not passive. Observing a system requires interaction, and interaction introduces disturbance. Even when this disturbance is negligible by everyday standards, chaotic systems do not ignore it. They incorporate it. The act of measuring becomes part of the system's history, subtly altering the conditions from which the future unfolds. Precision, in this sense, does not stand outside the system, it becomes entangled with it. This entanglement reveals a deeper limitation. Complete knowledge of a system's state is not just practically unreachable, but conceptually undefined. To know a system's initial conditions perfectly would require specifying them with infinite detail, across infinite scales. Nature does not offer such clarity. Reality unfolds in gradients, approximations, and continuous variation. Chaos theory shows that demanding perfect knowledge is not a scientific ambition, but a logical impossibility. As a result, the failure of long-term prediction is not a temporary obstacle awaiting better tools. It is a permanent feature of certain systems. Precision can delay uncertainty, but it cannot defeat it. The future remains determined, yet increasingly opaque, shaped by details that slip away the moment one tries to capture them. In chaotic systems, the limits of measurement are not technological boundaries. They are reflections of how deeply the system listens to its own smallest details, carrying them forward into an unknowable future. Every attempt to predict the future of a system carries within it an unspoken assumption that the future exists as a clearly defined extension of the present, waiting to be uncovered with enough effort. In chaotic systems, this assumption quietly breaks down. Prediction does not fail because the system becomes erratic or because the laws governing it suddenly change. It fails because the system amplifies uncertainty at a rate that outpaces any possible gain in knowledge. The future does not vanish, but it recedes, slipping beyond the reach of precise description as time moves forward. This retreat of predictability follows a recognizable pattern. At first, forecasts remain accurate, reinforcing confidence in both the model and the observer. Small errors remain small, and the system appears well behaved. But as time progresses, these errors grow, not in proportion to time, but exponentially. Each step forward carries a larger uncertainty than the last, until the range of possible futures expands beyond any meaningful resolution. The point at which this happens marks a horizon, a boundary beyond which prediction loses its usefulness. This horizon is not arbitrary, nor is it imposed by human limitations alone. It is a structural feature of chaotic systems. No improvement in measurement, no refinement of equations can remove it entirely. Precision can push the horizon slightly farther, but it can never eliminate it. There will always be a moment beyond which multiple futures become indistinguishable, overlapping in ways that make precise forecasting impossible. The system continues to evolve, but its future can no longer be traced as a single, definite path. Beyond this horizon, the language of prediction must change. Instead of asking what will happen, one must ask what can happen. Deterministic certainty gives way to statistical description, where patterns, tendencies, and probabilities replace exact outcomes. This shift does not signal a failure of science, but a maturation of it. Understanding becomes less about control and more about mapping the space of possibilities within which the system moves. The existence of a predictive horizon also carries philosophical weight. It challenges the belief that complete knowledge of the present grants mastery over the future. In chaotic systems, the present does not contain a single, extractable future. It contains many, each separated by differences too subtle to be fully known. The future unfolds lawfully, yet without transparency, shaped by details that no observer can ever capture in full. In this way, the natural horizon of prediction defines the limits of foresight without undermining the existence of order. The universe remains governed by rules, But those rules do not promise certainty. They promise structure without predictability, coherence without foresight. The future continues to form, moment by moment, beyond the horizon where precise knowledge ends, leaving behind a world that is lawful, sensitive, and permanently resistant to complete anticipation. Weather was one of the first real-world systems to reveal the true consequences of chaos. At a glance, the atmosphere appears vast, continuous, and governed by well-understood physical laws. Temperature gradients, pressure differences, humidity, and wind all follow equations rooted in classical physics. Nothing about the atmosphere is random in principle. And yet, despite this foundation, weather remains notoriously difficult to predict beyond a short window of time. This contradiction is not a failure of science, but a direct expression of chaos in action. The atmosphere is an interconnected system where countless variables interact simultaneously across multiple scales. A small change in temperature in one region influences air pressure, which alters wind patterns, which in turn affect moisture distribution elsewhere. Each interaction feeds back into the system, reshaping the conditions from which the next moment emerges. These interactions do not occur in isolation. They overlap, reinforce, and distort one another, creating a continuously evolving structure that resists simplification. What makes weather especially sensitive is the speed at which information travels through the system. Air moves, heat transfers, and moisture condenses and evaporates constantly, allowing tiny disturbances to propagate rapidly. A barely measurable fluctuation can spread, influencing regions far removed from its origin. Over time, these influences compound, making the system increasingly sensitive to details that cannot be fully observed or measured. The atmosphere remembers its past too well to allow long-term certainty. This sensitivity explains why weather forecasts degrade so quickly. Short-term predictions often perform remarkably well, capturing the general behavior of storms, temperature shifts, and wind patterns. But as time extends forward, uncertainty grows exponentially. Slight errors in initial measurements, unavoidable in a system of such scale, are amplified through nonlinear interactions. Eventually, the forecast no longer represents a single future, but a range of possible scenarios, each consistent with the same underlying laws. Importantly, this unpredictability does not imply instability. The atmosphere does not spiral out of control. It remains bounded, cycling through recognizable patterns and seasonal rhythms. Storms form and dissipate, climates persist, and large-scale structures endure. Chaos does not destroy order here. It reshapes it into a form that is dynamic rather than fixed, structured yet perpetually sensitive to its own evolving state. In this way, weather serves as a living demonstration of chaos theory's core insight. A system can be lawful, continuous, and deeply structured while still defying long-term prediction. The atmosphere follows rules without exception, yet its future cannot be pinned down beyond a certain horizon. Weather reminds us that unpredictability is not a sign of disorder, but a natural consequence of sensitivity unfolding within a vast and interconnected system. Weather forecasts do not fail because scientists misunderstand the atmosphere, nor because the equations describing air motion are incomplete. They fail because the atmosphere amplifies uncertainty faster than prediction can contain it. At the moment a forecast is made, it is based on a snapshot of the atmosphere, assembled from millions of measurements taken across the globe. This snapshot is detailed, sophisticated, and remarkably accurate by historical standards, yet it is still incomplete. Tiny gaps remain, tiny uncertainties that seem irrelevant at first, but which the atmosphere will not ignore. As time moves forward, these uncertainties begin to grow. Each interaction between temperature, pressure, and moisture slightly reshapes the system's evolution. These reshaped states then interact again, producing further divergence. The process is not linear. Errors do not grow steadily. They accelerate. What begins as a barely noticeable deviation spreads through the system, altering wind patterns, shifting pressure systems, and changing the timing of condensation and evaporation. The atmosphere carries these differences forward, embedding them into every future state. Forecast models attempt to manage this by running many simulations at once, each starting with slightly different initial conditions. This technique does not remove uncertainty, it reveals it. When the simulations agree, confidence is high. When they diverge, the forecast becomes probabilistic rather than precise. This divergence is not a failure of modeling. It is a direct reflection of the atmosphere's sensitivity. The models are not disagreeing because they are wrong, but because the system allows multiple futures to unfold from nearly identical beginnings. Over longer timescales, this divergence becomes unavoidable. After several days, small uncertainties expand to the point where different simulations describe entirely different weather patterns. A storm that appears inevitable in one scenario may weaken or vanish in another. Temperature forecasts that once aligned drift apart. At this stage, the forecast no longer describes a single future. It describes a landscape of possibilities, all consistent with the same physical laws, yet incompatible with one another in detail. This is why improving forecasts is a matter of extending reliability, not achieving certainty. Better instruments, denser measurement networks, and faster computers can push the predictive horizon outward, but only slightly. They cannot eliminate it. The atmosphere's sensitivity ensures that there will always be a point beyond which precise prediction collapses. The system remembers too much, responds too finely, and evolves too quickly for long-term certainty to survive. In this sense, weather forecasting reveals a deeper truth about chaotic systems. Failure is not the exception. It is the expected outcome beyond a certain horizon. The atmosphere is not disobedient. It is exquisitely responsive. Its unpredictability is not a flaw, but a signature of its complexity. Each forecast succeeds only temporarily, before surrendering to the quiet and relentless growth of uncertainty that defines chaos in motion. At first, the distinction between weather and climate appears subtle, but it is essential to understanding how chaos operates on different timescales. Weather describes the immediate state of the atmosphere, the precise configuration of temperature, pressure, wind, and moisture at a given moment. Climate, by contrast, describes long-term patterns, averages, and statistical tendencies that emerge over extended periods of time. While weather is sensitive to tiny details and rapidly diverging conditions, climate reflects the broader structure within which those fluctuations occur. This difference explains why weather forecasts fail while climate models remain meaningful. Chaos undermines precise prediction of individual events, but it does not erase underlying patterns. The atmosphere may evolve along countless possible paths, yet those paths are constrained. They occupy a limited range of behavior shaped by energy balance, solar input, ocean circulation, and the physical properties of air and water. Within these constraints, short-term outcomes vary wildly, but long-term distributions remain stable and interpretable. Climate models do not attempt to predict the exact weather on a specific day years into the future. Instead, they describe how the statistical properties of weather change over time. They ask how often certain temperatures occur, how precipitation patterns shift, and how extremes become more or less frequent. Chaos prevents the identification of a single future state, but it allows the exploration of tendencies across many possible futures. In this way, uncertainty at the event level coexists with clarity at the pattern level. This coexistence reveals an important feature of chaotic systems. Unpredictability and order are not opposites. They operate at different scales. Short-term behavior remains sensitive and unstable, while long-term structure persists. The system fluctuates continuously, but those fluctuations are organized around enduring constraints. Climate emerges not in spite of chaos, but through it, shaped by countless unpredictable events that collectively form stable trends. Misunderstanding this distinction often leads to confusion. It is tempting to assume that if tomorrow's weather cannot be predicted reliably beyond a certain point, then long-term climate projections must also be meaningless. Chaos theory shows why this conclusion is flawed. The inability to track exact trajectories does not eliminate the ability to describe the space within which those trajectories unfold. Climate does not require certainty about individual outcomes. It requires consistency in the forces that shape the system over time. In this sense, climate represents order within chaos. It is the slow, persistent structure that emerges from the rapid, unpredictable motion of the atmosphere. Weather dances unpredictably within this structure, sensitive to every small disturbance, while climate reflects the deeper constraints that guide that motion. Chaos does not dissolve climate. It defines the boundary between what can be predicted precisely and what can only be understood statistically, revealing a world that is both restless and remarkably coherent. Extreme weather events reveal chaos in its most visible and unsettling form. Heat waves, intense storms, prolonged droughts, and sudden floods appear not as isolated anomalies, but as expressions of a system operating near the edges of its constraints. In a chaotic atmosphere, small variations do not simply alter average conditions. They can push the system toward thresholds where behavior changes abruptly. A slight increase in temperature, a modest shift in circulation, or a subtle change in moisture distribution can tip the balance, transforming ordinary fluctuations into extreme outcomes. What makes extremes especially difficult to predict is their dependence on timing and alignment. In chaotic systems, it is not enough for conditions to be favorable. Multiple factors must converge in a precise sequence. When they do, feedback loops intensify the system's response. Heat dries the land, dry land amplifies heat. Warm air holds more moisture, releasing more energy when condensation occurs. These reinforcing processes magnify initial differences, allowing extremes to grow rapidly from conditions that might otherwise appear unremarkable. Chaos also ensures that extremes are unevenly distributed. They do not increase smoothly or uniformly. Instead, they emerge sporadically, clustered in time and space. Long periods of relative stability may be interrupted by sudden bursts of intense activity. This irregularity is not random. It reflects the system's sensitivity to its evolving state. The atmosphere carries forward the memory of past conditions, storing energy and imbalance until a configuration arises that allows rapid release. As the climate shifts, this sensitivity becomes more pronounced. Changes in average conditions alter the boundaries within which weather unfolds. The system does not simply warm or cool. It reorganizes. Patterns of circulation adjust, thresholds shift, and feedback mechanisms operate in new regimes. Chaos ensures that these adjustments are non-linear. Small changes in forcing can lead to disproportionate changes in outcomes, increasing the frequency or intensity of extremes without a simple linear relationship. This behavior challenges intuitive expectations. It is tempting to assume that gradual changes produce gradual effects. In chaotic systems, gradual forcing can produce abrupt responses. Extremes emerge not as outliers, but as natural consequences of amplified sensitivity. The system does not warn clearly before crossing thresholds. It transitions suddenly, revealing new modes of behavior that were always possible, but rarely realized under previous conditions. In this way, extreme weather events illustrate the deeper lesson of chaos theory. The atmosphere is not fragile, but it is responsive. Its most dramatic expressions arise not from singular causes, but from the accumulation and amplification of countless small influences. Extremes are not exceptions to the system's rules. They are the rules unfolding under conditions where sensitivity, feedback, and timing align, exposing the powerful and often unpredictable consequences of chaos in motion. Chaos is not confined to the sky above us. It is woven into the structure of nature itself, quietly shaping patterns that appear stable on the surface while remaining deeply sensitive beneath. Rivers carve landscapes, clouds drift and dissolve, hearts maintain rhythm, and brains generate thought, all according to physical and biological laws. Yet none of these systems behave in a perfectly regular way. They fluctuate, adapt, and respond, carrying within them a delicate balance between order and unpredictability that defines chaotic behavior in the natural world. Consider the flow of a river as it moves around rocks and bends in the land. The governing laws of fluid motion are well known, yet the water never follows the same path twice. Tiny variations in speed, pressure, and surface texture create swirling eddies and branching currents that constantly reshape the flow. These patterns are not random. They emerge from deterministic interactions repeated endlessly, amplifying small differences until the river's motion becomes richly complex and impossible to predict in detail. Clouds offer another striking example. Formed from countless microscopic droplets and ice crystals, they evolve through interactions between temperature, pressure, and moisture. A slight change in altitude or sunlight can alter how a cloud grows, thins, or dissipates. Over time, these small influences accumulate, producing forms that are endlessly varied yet recognizable. Clouds obey physical laws without exception, but their shapes and lifespans resist precise prediction, reflecting the same sensitivity that defines chaotic systems elsewhere. This pattern extends into living systems as well. The beating of the human heart, for example, is not perfectly regular. Healthy hearts display subtle variability, responding continuously to internal and external conditions. This variability is not a flaw, it is a sign of adaptability. When the system becomes too regular, it often signals pathology. Chaos here supports resilience, allowing the system to adjust fluidly rather than locking into rigid, fragile patterns. In the brain, chaos appears at an even deeper level. Neurons fire in complex, interconnected networks, influenced by countless signals arriving from within and beyond the body. Small changes in neural activity can cascade through these networks, altering perception, thought, and behavior. The brain's ability to think, learn, and adapt relies on this sensitive balance. Too much order would make it inflexible. Too much randomness would make it incoherent. Chaos occupies the space between, enabling creativity and responsiveness. Across these systems, a common theme emerges. Nature does not favor perfect regularity or complete disorder. It operates in a dynamic regime where small influences matter and patterns emerge without settling into repetition. Chaos is not an anomaly within nature. It is one of its primary organizing principles, allowing systems to remain structured, adaptable, and alive. In this balance between predictability and surprise, the natural world reveals a deeper kind of order, one that unfolds continuously without ever fully repeating itself. Rivers provide one of the clearest and most tangible expressions of chaos in nature. From a distance, a river may appear stable, even timeless, following a familiar path carved into the landscape. Yet, when observed closely, its motion is never still and never repeats itself. Every ripple, eddy, and current emerges from countless interactions between water, gravity, and terrain. The laws governing this flow are precise, but their repeated application produces patterns so sensitive that no two moments are ever exactly the same. As water moves downstream, it continuously encounters resistance and variation. Rocks, sediment, changes in slope, and subtle shifts in volume alter the flow in small but persistent ways. These variations do not cancel out. They interact. A minor deflection in current reshapes pressure elsewhere, which then influences downstream motion, creating branching streams and swirling vortices. Over time, these interactions give rise to complex geometries that cannot be predicted from initial conditions alone, despite being fully determined by physical law. This branching behavior extends beyond individual rivers to entire river networks. Tributaries split and rejoin, forming fractal-like patterns that repeat across scales. Small streams resemble larger rivers in structure, reflecting the same underlying dynamics operating at different magnitudes. Chaos plays a central role here, ensuring that while the overall pattern remains recognizable, its specific details remain unpredictable. The river network evolves as a living system, sensitive to both immediate conditions and long-term history. Importantly, the geometry of river flow is not arbitrary. The system explores a constrained space of possibilities defined by energy minimization and gravitational pull. Chaos does not allow the river to take any path. It allows it to choose among many viable ones, each shaped by accumulated interactions over time. This balance between freedom and constraint gives rise to landscapes that are rich in variation, yet coherent in form, shaped by processes that remember their past without repeating it. As conditions change, the river responds. Seasonal shifts in rainfall, gradual erosion, and sudden floods alter the system's parameters. Each change introduces new sensitivities, redirecting flow and reshaping channels. A single flood can carve a new path, abandoning an old one that took centuries to form. These transitions are not random events imposed from outside. They are the natural outcomes of a system operating near thresholds where small changes can unlock entirely new configurations. In this way, rivers illustrate a central lesson of chaos theory. Order does not require rigidity. Structure does not demand repetition. The river's path is lawful yet flexible, shaped by countless small influences that accumulate and interact over time. Chaos allows the river to remain responsive to its environment, continuously adapting while preserving an underlying coherence. What emerges is not disorder, but a living geometry, carved by sensitivity and sustained by flow. Clouds appear calm and almost weightless when viewed from a distance, drifting slowly across the sky in familiar shapes. Yet within them, the atmosphere is in constant motion. Warm air rises, cool air sinks, moisture condenses and evaporates, and energy is exchanged continuously. These processes interact at countless scales simultaneously, creating a system that is both structured and endlessly variable. The laws governing cloud formation are well understood, but their visible forms resist precise prediction because they emerge from chaotic interactions unfolding moment by moment. Turbulence lies at the heart of this behavior. As air flows, it does not move smoothly in straight lines. It twists, curls, and breaks into vortices of many sizes, each influencing the others. Small swirls feed larger ones, while larger structures fragment into finer detail. This cascade of motion ensures that information travels rapidly through the system, allowing tiny variations in temperature or velocity to spread and reshape the entire cloud. The result is a form that is coherent yet unstable, recognizable yet never fixed. This is why clouds seem familiar without ever repeating themselves. A cumulus cloud may resemble another, but no two are identical. Their edges ripple and dissolve, shaped by sensitivity to sunlight, altitude, and surrounding air currents. Each moment carries forward the imprint of previous interactions, layering new structure onto old. The cloud does not forget its past, but it does not preserve it in a simple way. It transforms it, folding history into form through continuous motion. Turbulence also explains why clouds can change so quickly. A slight shift in wind or temperature can alter the balance between growth and dissipation. Regions of rising air may strengthen while others collapse. What appears stable can suddenly unravel, not because an external force intervened, but because the system crossed an internal threshold. Chaos ensures that these transitions are abrupt and difficult to anticipate, emerging naturally from the system's evolving state. Despite this unpredictability, clouds are not formless. They occupy specific regimes defined by atmospheric conditions. Certain patterns recur because the constraints shaping them remain consistent. Chaos does not eliminate structure here, it generates it dynamically. The cloud's form is a snapshot of an ongoing process, a visible record of countless interactions occurring faster than the eye can follow. Order exists, but only as motion, never as permanence. In this sense, clouds offer a quiet lesson in how chaos shapes beauty in nature. Their ever-changing forms arise not from randomness, but from sensitivity and flow. They demonstrate how systems can remain bounded and recognizable while continuously reinventing themselves. Chaos allows clouds to exist as living structures, suspended between formation and dissolution, revealing a world where change itself becomes the most stable pattern of all. At first glance, the human body appears to function through regular, repeating rhythms. The heart beats, the lungs breathe, hormones rise and fall, and neural signals travel along familiar pathways. This apparent regularity suggests stability and control, a machine-like precision keeping the body in balance. Yet beneath this surface, biological systems are anything but perfectly regular. Healthy bodies operate in a state of controlled variability, where small fluctuations are not only present, but essential to survival and adaptation. The rhythm of the heart provides one of the clearest examples of this principle. A healthy heartbeat is not metronomic. The intervals between beats vary subtly from moment to moment, responding continuously to changes in posture, emotion, breathing, and metabolic demand. This variability reflects a complex network of feedback loops involving the nervous system, hormones, and the heart itself. Chaos emerges here not as disorder, but as flexibility, allowing the system to adjust instantly to internal and external conditions. When this variability disappears, the consequences are often serious. Hearts that beat with rigid regularity are less adaptable and more vulnerable to sudden failure. Too much order becomes a sign of fragility rather than strength. Chaos, in this context, supports resilience. It allows the system to explore a range of responses without committing to a single rigid pattern. The body remains poised, responsive, and capable of absorbing shocks because it never fully settles into predictability. This principle extends beyond the heart to other biological rhythms. Breathing patterns fluctuate with activity, emotion, and environment. Hormonal cycles shift in response to stress, light, and social cues. Neural activity in the brain unfolds through complex, non-linear dynamics, where small changes in input can alter perception, mood, or thought. These systems do not function by repeating identical cycles. They function by continuously adjusting, guided by feedback and sensitivity rather than rigid control. Biological chaos also plays a crucial role in coordination. Countless subsystems must remain synchronized without being locked together. Muscles, nerves, and organs communicate through signals that are precise yet flexible, allowing coordination without rigidity. Chaos enables this balance. It prevents the system from becoming trapped in fixed patterns while maintaining coherence across scales. The body behaves less like a machine and more like an adaptive process, constantly negotiating stability through variation. In this way, the human body reveals chaos, not as a threat to order, but as one of its deepest foundations. Life persists by remaining sensitive, responsive, and slightly unpredictable. Biological rhythms thrive in the space between regularity and randomness, where chaos allows systems to remain alive rather than merely functional. The body does not seek perfect control. It seeks balance through continuous, delicate variation, unfolding moment by moment in a quiet dance of order and uncertainty. Human life often feels deliberate and directed, shaped by conscious choices and carefully considered plans. We tend to believe that our paths are determined by major decisions, dramatic events, and clear turning points that announce their importance as they happen. Yet when examined closely, the structure of a life reveals something far more fragile and subtle. The trajectory of a person's experiences is rarely shaped by singular moments alone. It emerges from a dense accumulation of small, often unnoticed decisions that quietly redirect the flow of events over time. A delayed train, a casual conversation, a choice made under fatigue or distraction can alter what follows in ways that are impossible to foresee. These moments carry little weight in isolation. At the time they occur, they appear interchangeable, easily forgotten. But once embedded into the sequence of events that follows, they become inseparable from everything that comes after. The system of a life, like any chaotic system, does not reset. It carries its history forward, allowing small variations to compound until they shape outcomes that feel inevitable in retrospect. This compounding effect explains why lives diverge so dramatically from nearly identical beginnings. Two people may share similar backgrounds, opportunities, and intentions, yet find themselves moving toward entirely different futures. The divergence does not require a single decisive fork in the road. It unfolds gradually through accumulated differences in timing, context, and response. Each small choice alters the conditions under which the next choice is made, creating a cascade of influence that grows quietly with time. Importantly, this process does not imply randomness or lack of agency. Human lives are not governed by chance alone. They are structured by personality, environment, and intention. But within that structure, sensitivity plays a powerful role. Emotional states, fleeting impressions, and momentary constraints can shift decisions just enough to redirect long-term trajectories. The future remains lawful, shaped by causes and effects, yet deeply sensitive to details that resist conscious control. As time passes, these compounded differences solidify into patterns. Careers form, relationships develop, habits take root. Looking backward, the path appears coherent, even purposeful. The mind constructs narratives that link outcomes to identifiable causes, smoothing over the countless minor influences that made those outcomes possible. This retrospective clarity creates the illusion that the future was always heading in that direction, obscuring the fragile sensitivity that guided it there. In this way, the Kellebeck effect operates quietly within human life. It does not announce itself through dramatic upheaval. It works through accumulation, timing, and context, shaping futures through details too small to register at the moment they occur. Lives unfold not as linear progressions toward fixed goals, but as evolving systems, sensitive to beginnings, responsive to feedback, and perpetually shaped by the subtle architecture of their own history. Human lives are filled with encounters that appear accidental, moments that seem to arise without intention or design. A meeting that happens because of a minor delay, a conversation initiated out of politeness, a message sent at an unusual hour. At the time, these events carry no clear signal of importance. They register as ordinary, interchangeable experiences, easily dismissed as coincidence. Yet once they occur, they alter the state of the system, reshaping the conditions under which all subsequent events unfold. What gives these encounters their power is irreversibility. Once a moment passes, it cannot be undone. The system does not return to its previous state. New information has entered, new relationships have formed, new possibilities have opened while others quietly close. Even if the encounter seems inconsequential, it shifts timing, perception, and opportunity just enough to redirect what follows. In a life shaped by sensitivity, there is no true reset. Every interaction becomes part of the permanent record. This irreversibility explains why chance encounters often gain significance only in retrospect. Looking backward, it becomes easy to identify a meeting as pivotal, a conversation as transformative. At the moment it occurred, nothing about it demanded attention. Its importance was not inherent. It emerged through accumulation. One encounter leads to another. One decision alters the context of the next, and over time a path takes shape that feels deliberate, even though it was assembled from fragments that appeared accidental. These processes mirror chaotic systems in nature, where small perturbations are absorbed and amplified through feedback. In human life, feedback takes the form of memory, emotion, and habit. An encounter influences how a person thinks, which alters how they act, which reshapes the opportunities they notice. Each step feeds into the next, creating a loop that reinforces certain directions while quietly excluding others. The system narrows its future not through conscious choice alone, but through accumulated response. Importantly, this does not mean that life is governed by randomness. Chance encounters do not override agency, they interact with it. Personality, values, and prior experience determine how an encounter is interpreted and acted upon. Yet even within this structure, timing and context remain decisive. A meeting that changes everything at one moment might have no effect at another. Sensitivity ensures that outcomes depend not only on what happens, but on when and under what conditions it happens. In this way, human lives unfold along irreversible paths, shaped by a dense web of encounters and responses. The Kellebeck effect does not operate through dramatic disruptions, but through quiet redirections that accumulate over time. What feels like destiny often emerges from chance filtered through sensitivity, leaving behind a future that could not have been predicted, yet feels strangely coherent once it has already taken shape. Human memory has a peculiar relationship with the past. It does not simply record events as they happened. It interprets them, reorganizes them, and assigns meaning retroactively. When outcomes are disappointing or painful, the mind instinctively searches for branching points, moments where a different choice might have produced a different life. Regret emerges from this search, fed by the belief that the past contained clear alternatives that were consciously rejected. Chaos theory complicates this belief by revealing how fragile and undefined those alternatives truly were. In a sensitive system, the past does not contain a small number of clearly separated futures. It contains an immeasurable number of possibilities, each dependent on conditions that were never fully visible at the time. The idea of a single wrong turn assumes that the system could have been rewound and replayed with one variable changed while everything else remained constant. In reality, no such replay is possible. Changing one decision would have altered the emotional state, timing, context, and subsequent choices in ways that cannot be isolated or predicted. Memory intensifies this illusion by simplifying complexity. It compresses long chains of influence into symbolic moments, assigning disproportionate weight to specific decisions while ignoring the countless small factors that made those decisions meaningful. A conversation remembered as pivotal may have mattered only because of events that preceded it and conditions that followed it. Remove those surrounding influences, and the same moment might dissolve into insignificance. The mind reconstructs the past as a clean narrative, erasing the sensitivity that shaped it. This reconstruction creates the impression that alternative futures were stable and accessible, waiting just beyond reach. In chaotic systems, such stability does not exist. Small differences do not lead to slightly different outcomes. They lead to entirely different trajectories that cannot be compared meaningfully. The future that did not happen is not a coherent version of the present with one detail changed. It is an entirely different unfolding, shaped by interactions that were never allowed to occur. Regret, then, is rooted in a misunderstanding of how sensitive systems evolve. It assumes that control was greater than it actually was, and that the future was more clearly defined than it ever could be. This does not diminish responsibility or agency, but it reframes them. Decisions mattered, but not in isolation. They mattered as part of an evolving context that no individual could fully perceive or manage at the time. In this light, regret becomes less a judgment on past choices and more a reflection of hindsight applied to an unknowable system. The feeling arises not because the wrong future was chosen, but because the mind insists on imagining futures that were never fully available. Chaos reveals a quieter truth. The past did not contain a clear map of alternate lives. It contained sensitivity, uncertainty, and paths that could only be traced once they had already been taken. The idea of control occupies a central place in how humans understand their lives. We are taught, implicitly and explicitly, that careful planning, disciplined effort, and rational decision-making grant mastery over the future. Control becomes a moral concept as much as a practical one, tied to responsibility and self-worth. Chaos challenges this framework without dismissing it. It reveals that control is always partial, bounded by sensitivity, context, and forces that remain invisible at the moment decisions are made. In a chaotic system, responsibility does not vanish, but it changes form. Actions still matter. Choices still shape what follows. Yet their effects cannot be isolated or traced forward with certainty. A decision does not move the future along a single predictable line. It reshapes the conditions under which countless other influences interact. Responsibility, then, lies not in commanding outcomes, but in participating honestly in a process whose full consequences can never be known in advance. This realization can feel unsettling. If the future cannot be controlled, then effort may seem fragile, even futile. But chaos does not suggest helplessness. It suggests humility. It invites a shift away from the illusion of total control toward an acceptance of limited influence. Within that limit, intention still matters, direction still matters. But they operate alongside sensitivity rather than above it, shaping tendencies rather than guaranteeing results. Letting go, in this context, does not mean disengagement or passivity. It means releasing the expectation that life must unfold according to a precise plan. It means recognizing that uncertainty is not a personal failure, but a structural feature of complex systems. When control is loosened, attention shifts from outcome to process, from prediction to presence. Action becomes an expression of values rather than a demand for certainty. This perspective reframes success and failure as well. Outcomes are no longer absolute measures of correctness. They are snapshots of an unfolding process shaped by countless interacting factors. A choice can be thoughtful and still lead to unexpected difficulty. Another can be imperfect and still open unforeseen possibilities. chaos dissolves the myth that the future rewards perfect calculation. It reveals a world where responsiveness and adaptability often matter more than rigid foresight. In accepting these limits, a quieter form of freedom emerges. The pressure to foresee every consequence begins to fade. Responsibility remains, but it is grounded in intention rather than prediction. Life unfolds as a sensitive system shaped by action, context, and chance without offering guarantees. Letting go does not remove meaning. It allows meaning to arise from engagement with uncertainty itself, where control is partial, influence is real, and the future remains open in ways that can only be understood once it has already arrived. When chaos is extended beyond weather, biology, and human life, it does not disappear, it expands. The universe itself unfolds through systems that are lawful, interconnected, and profoundly sensitive to their own histories. Galaxies form, stars ignite, planets settle into orbits, all governed by well-defined physical principles. Yet the large-scale structure of the universe is not rigid or perfectly symmetrical. It carries traces of fluctuation, variation, and amplification that echo the same chaotic sensitivity found in smaller systems. In the early universe, conditions were nearly uniform, with only tiny differences in density and temperature spread across vast distances. These differences were unimaginably small, barely distinguishable from one another. Yet over immense stretches of time, gravity amplified them. Regions that were slightly denser attracted more matter, becoming seeds for galaxies and clusters, while emptier regions grew into vast cosmic voids. The universe did not require dramatic disturbances to create structure. It listened to its smallest irregularities and allowed them to grow. This process reveals chaos, operating on a cosmic scale. The laws of physics did not change from place to place. The outcomes did. Slight variations in initial conditions shaped entirely different regions of space, leading to a universe rich in structure without ever violating determinism. The large-scale order we observe today emerged not from perfect symmetry, but from sensitivity unfolding over time. The universe became complex because it was responsive, not because it was disordered. Importantly, this sensitivity does not imply randomness. The universe does not behave like a roll of dice. It follows strict rules at every step. But those rules interact in ways that magnify difference rather than erase it. As time progresses, the imprint of early fluctuations becomes more pronounced, woven into the fabric of cosmic evolution. What we observe now is not chaos replacing order, but chaos generating it, shaping a universe that is structured yet irreducibly unique. This perspective challenges the intuition that order must arise from uniformity. In chaotic systems, uniformity is unstable. It invites differentiation. Small asymmetries are not corrected, they are amplified. The universe does not converge towards sameness, it diversifies. Stars vary in size and lifespan, galaxies differ in shape and behavior, and planetary systems follow distinct evolutionary paths, all emerging from a common set of rules applied to slightly different beginnings. In this way, the cosmos reflects the same principle seen in rivers, hearts, and lives. It evolves by remembering its past and responding to it with sensitivity. The universe does not impose a single outcome on itself. It allows countless possibilities to unfold within lawful constraints. Chaos here is not noise at the edge of understanding. It is a fundamental mechanism through which structure, diversity, and complexity arise on the grandest scale imaginable. At a distance, the universe can appear random, filled with events that seem to occur without pattern or intention. Stars explode, galaxies collide, particles fluctuate, and outcomes often defy simple explanation. This appearance has led many to assume that randomness lies at the heart of cosmic behavior. Chaos theory invites a more careful distinction. It suggests that unpredictability does not automatically imply randomness, and that a system can behave in ways that are deeply uncertain while remaining fully governed by deterministic laws. Randomness, in its strict sense, implies the absence of underlying cause. A truly random event has no dependence on prior states and cannot be derived from them, even in principle. Chaotic systems do not behave this way. Every moment in a chaotic system emerges from the one before it according to fixed rules. Nothing appears without cause. The difficulty lies not in the absence of law, but in the system's sensitivity to details that cannot be fully known or controlled. The universe does not roll dice, it responds. This distinction becomes especially important at cosmic scales, where immense time spans amplify tiny differences. Small fluctuations in energy, density, or position do not disappear into insignificance. They persist, shaping trajectories that diverge dramatically over billions of years. The resulting diversity of cosmic structures can look random, but it is not. It is the outcome of deterministic processes unfolding under conditions of extreme sensitivity. What appears arbitrary is often the visible trace of differences too small to reconstruct after the fact. The confusion between randomness and chaos arises because both defeat prediction. From the perspective of an observer, the future of a chaotic system may be as unknowable as that of a random one. Yet their internal logic is entirely different. Random systems erase the past. Chaotic systems preserve it too well. Every detail is remembered, carried forward, and amplified, embedding history into the present. The universe's unpredictability stems not from forgetfulness, but from an excess of memory. This excess of memory reshapes how order is understood. Order no longer means repetition or uniformity. It means consistency of law across diversity of outcome. The same physical principles operate everywhere, yet they produce a cosmos rich in variation because they respond faithfully to initial conditions that were never perfectly identical. Determinism ensures coherence, while chaos ensures differentiation. Together, they generate a universe that is lawful without being predictable, structured without being monotonous. In recognizing this balance, the universe appears neither arbitrary nor rigid. It occupies a middle ground where outcomes are constrained but not prescribed, where laws guide evolution without dictating exact results. Randomness is not the engine of cosmic complexity. Sensitivity is. The universe unfolds through deterministic rules applied to an ever-shifting state, allowing order and unpredictability to coexist without contradiction, shaping a cosmos that remains intelligible even as its future resists precise anticipation. Time appears to move in only one direction. We remember the past, experience the present, and anticipate the future, but never the reverse. This asymmetry, often called the arrow of time, has long puzzled physicists because the fundamental laws of nature do not prefer a direction. At the microscopic level, equations work just as well forward as backward. Chaos theory offers a crucial insight into how this directional flow emerges, not from the laws themselves, but from sensitivity unfolding over time within complex systems. In a sensitive universe, small differences at the beginning are not erased. They are preserved and amplified, creating an irreversible divergence between past and future. Once a system evolves, it cannot retrace its exact path because the information required to do so has been stretched, dispersed, and embedded across countless interactions. The system remains deterministic, but its history becomes unrecoverable in detail. Time gains direction, not through violation of physical law, but through the practical impossibility of reversal in a world that remembers too much. On cosmic scales, this irreversibility becomes profound. As the universe expands, structures form through the amplification of early fluctuations. Galaxies cluster, stars ignite, and matter organizes itself into increasingly complex arrangements. Each step forward locks in previous differences, making the exact reconstruction of earlier states impossible. Even if the laws allowed reversal, the sensitivity of the system ensures that any attempt to move backward would require infinite precision, a requirement nature does not permit. This sensitivity also explains why the future feels open while the past feels fixed. The past represents a single realized trajectory shaped by countless amplified differences that can no longer be altered. The future, by contrast, exists as a space of possibilities, constrained by law but not yet selected. Chaos ensures that tiny present uncertainties will grow, preventing the future from collapsing into a single, knowable outcome. Time flows forward as uncertainty unfolds, not because the universe is random, but because it is exquisitely responsive. As the arrow of time advances, information spreads rather than concentrates, energy disperses, structures evolve, and sensitivity ensures that details are carried outward into larger patterns. This spreading of influence aligns chaos with the thermodynamic tendency toward increasing entropy without reducing it to disorder. Entropy here is not mere decay, it is the record of irreversible unfolding, where the past is continuously folded into the present in ways that cannot be undone. In this view, time is not simply a backdrop against which events occur. It is an active dimension shaped by sensitivity and accumulation. Chaos gives time its texture, transforming lawful evolution into an irreversible narrative. The universe does not march forward blindly. It listens to its own history, amplifies its smallest beginnings, and moves irreversibly into futures that are determined in principle, yet forever inaccessible in detail. At first encounter, chaos appears to undermine the very idea of order. It replaces certainty with unpredictability, precision with divergence, and foresight with limitation. Yet as chaos theory matured, a quieter realization began to take shape. Beneath the apparent instability of chaotic systems lies a form of order that is not immediately visible. This order does not express itself through repetition or symmetry, but through constraint. Chaotic systems do not wander freely. They remain confined within invisible boundaries that shape their behavior over time. These boundaries reveal themselves through patterns that emerge only when systems are observed across long durations. While individual trajectories diverge rapidly, the overall structure remains stable. The system explores a limited space of possibilities, tracing intricate paths that never repeat exactly. yet never escape their underlying framework. This suggests that chaos does not destroy order. It conceals it within motion, embedding structure into change rather than freezing it into permanence. This hidden order challenges a deep-seated assumption about understanding. Humans are drawn to static representations, to forms that can be captured, categorized, and predicted. Chaos resists this preference. It demands a different kind of comprehension, one that accepts variability as a feature rather than a flaw. Understanding shifts from forecasting outcomes to recognizing patterns of behavior, from predicting exact futures to mapping the space within which those futures unfold. In this sense, chaos reveals an order that is richer than predictability. It allows systems to remain adaptable, responsive, and creative. Rigid order collapses under disturbance. Chaotic order absorbs it. The system does not cling to a single path, but navigates among many, guided by constraints that preserve coherence without enforcing uniformity. Stability emerges not from control, but from flexibility sustained over time. This perspective reshapes how the universe itself is interpreted. The cosmos no longer appears as a machine grinding toward a predetermined end, nor as a random process drifting without direction. It appears as a sensitive system unfolding within lawful boundaries, continuously generating structure through interaction and amplification. Diversity, complexity, and novelty arise not in spite of order, but because order allows sensitivity to operate freely. In recognizing this deeper order, chaos becomes less threatening and more illuminating. It shows that uncertainty is not the absence of meaning, but the condition under which meaning evolves. The universe remains intelligible without being predictable, coherent without being rigid. Beneath the restless motion of chaotic systems lies a quiet architecture, shaping possibilities without dictating outcomes, revealing a world where order and unpredictability are not opposites, but partners in the ongoing unfolding of reality. Human thought is deeply shaped by the desire for control. From early childhood, we learn to associate understanding with mastery, prediction with safety, and planning with success. To know what will happen is to feel protected against uncertainty. This belief becomes so ingrained that it often goes unquestioned, forming the silent foundation of how individuals, societies, and even scientific institutions approach the future. Chaos theory does not attack this desire directly. It quietly exposes its limits, revealing that control has always been more fragile than it appears. The illusion of control arises from short-term success. In many systems, prediction works well enough for long enough to reinforce confidence. Plans succeed, forecasts hold, and cause appears to follow effect in a neat and traceable way. These successes are real, but they are local. They operate within narrow windows of time and limited conditions. Chaos reveals that beyond these windows, the same mechanisms that allowed control to function begin to undermine it, amplifying uncertainty until precision dissolves. This illusion is strengthened by hindsight. Once events have unfolded, the mind reconstructs them into coherent narratives. Causes are identified, decisions are emphasized, and outcomes are explained as if they were the natural and foreseeable result of what came before. This reconstruction creates the impression that the future was always knowable, that control was possible but imperfectly applied. Chaos shows that this clarity is retrospective, not predictive. The story emerges only after uncertainty has already resolved into fact. Control also persists as a psychological necessity. Uncertainty produces discomfort, and the belief in control offers relief. Even when outcomes contradict expectations, the instinct is to refine the model rather than question the premise. Better data, better planning, better discipline are assumed to restore mastery. Chaos does not deny improvement. It reveals a ceiling. Beyond a certain point, refinement no longer reduces uncertainty in a meaningful way. The system remains sensitive, and control remains partial. Importantly, the illusion of control does not imply deception or ignorance. It is an adaptive response to a complex world. Humans evolved to act, not to remain paralyzed by uncertainty. The belief that actions shape outcomes is functionally useful, even when it overestimates precision. Chaos reframes this belief, separating influence from control. Actions matter, but they do not command the future. They participate in it, alongside countless other influences unfolding beyond awareness. In confronting the illusion of control, chaos does not leave emptiness behind. It replaces certainty with a different kind of understanding, one that accepts limits without surrendering meaning. The future becomes something to engage with rather than dominate, shaped by intention but not guaranteed by it. Control fades from absolute to relative, revealing a world where action remains significant, yet the unfolding of events always exceeds the reach of foresight. Living with uncertainty is not something humans are naturally trained to do. From the earliest moments of learning, certainty is rewarded and ambiguity is treated as a problem to be solved. Clear answers feel safe, while unanswered questions create tension. Chaos theory reframes this discomfort by revealing that uncertainty is not an error in understanding, but a permanent condition of complex systems. To live with uncertainty, then, is not to live in confusion, but to live in alignment with how reality actually unfolds. This shift requires a fundamental change in how meaning is constructed. When the future cannot be predicted precisely, meaning can no longer be anchored solely in outcomes. It must be rooted in process, intention, and responsiveness. Actions are no longer judged only by what they produce, but by how they are chosen and enacted within uncertain conditions. Chaos does not remove purpose. It relocates it, away from guaranteed results and toward engagement with the present moment as it evolves. Uncertainty also alters the emotional landscape of decision-making. Fear often arises from the belief that the future should be controllable and that failure reflects a personal inability to manage it. Chaos dissolves this expectation. It reveals that unpredictability is not a verdict on competence, but a feature of the system itself. When this is understood, anxiety shifts. The demand for certainty softens, making space for adaptability rather than rigid anticipation. Living with uncertainty encourages attentiveness. When outcomes cannot be fully foreseen, sensitivity to feedback becomes more important than adherence to fixed plans. The present moment gains weight, not as a stepping stone to a known future, but as the only point where influence is possible. Chaos favors those who listen, adjust, and respond, rather than those who attempt to impose control through prediction alone. Awareness replaces foresight as the primary guide. This way of living also reshapes resilience. In a predictable world, Resilience means resisting disturbance and returning to a prior state. In a chaotic world, resilience means absorbing change and reorganizing without losing coherence. The ability to adapt becomes more valuable than the ability to forecast. Systems that survive are not those that predict perfectly, but those that remain flexible in the face of unfolding uncertainty. Ultimately, living with uncertainty does not mean surrendering to randomness or abandoning responsibility. It means accepting limits while remaining engaged. Chaos invites a quieter confidence, one that does not depend on knowing what comes next. Meaning arises not from certainty about the future, but from participation in a process that is lawful, sensitive, and always unfolding beyond complete comprehension. When the future cannot be fully known, the question of meaning inevitably shifts. Meaning can no longer be derived from certainty or guaranteed outcomes, because those outcomes remain perpetually out of reach. Instead, meaning begins to emerge from orientation rather than destination. It becomes less about where events lead and more about how one moves through unfolding uncertainty. Chaos reveals that meaning does not require a predictable future. It requires coherence between intention, action, and awareness as time progresses. This perspective transforms how choices are understood. In a predictable world, choices are evaluated by their results. In a chaotic world, results are contingent, shaped by countless influences beyond perception. Choice regains its intrinsic value, not because it ensures a particular future, but because it expresses alignment with values in the present. Decisions become acts of participation rather than commands issued to the future, meaningful not for what they guarantee, but for what they embody. The unknowable future also dissolves the illusion that meaning must be permanent to be real. Humans often seek significance that endures unchanged, fixed against time and uncertainty. Chaos suggests a different model. Meaning can be temporary, situational, and evolving without being diminished. Like patterns in chaotic systems, it need not repeat to remain valid. It exists in the moment of engagement, shaped by context and sensitivity rather than permanence. This understanding softens the relationship between effort and expectation. When outcomes are uncertain, effort is no longer a transaction aimed at securing a specific result. It becomes an expression of commitment to a process whose full shape cannot be seen in advance. Action is freed from the burden of justification through prediction. One acts not because success is assured, but because participation itself carries significance. The unknowable future also reframes loss and disappointment. When the future is imagined as a single path that could have been secured with sufficient control, deviation feels like failure. Chaos dismantles this narrative. It reveals that the future was never singular or fully accessible. Loss does not represent the collapse of a guaranteed outcome, but the resolution of one among many possible trajectories. Grief remains real, but it is no longer anchored to the illusion of a knowable alternative. In this way, chaos offers a quieter foundation for meaning. It removes the demand that life conform to a comprehensible plan. Meaning arises instead from attentiveness, responsiveness, and coherence within uncertainty. The future remains open, not as a threat, but as a space where significance is continually formed through engagement with a world that is lawful, sensitive, and forever beyond complete foresight. To let the future remain open is not an act of resignation, but an act of understanding. It means recognizing that the future was never a fixed destination waiting to be reached, but an unfolding process shaped moment by sensitivity, interaction, and response. Chaos teaches that the future does not exist as a single line extending forward from the present. It exists as a field of possibilities, constrained by laws yet never fully specified in advance. Accepting this does not diminish life. It restores it to its true scale. Much of human tension arises from the attempt to close this openness prematurely. We seek certainty where none can exist, clarity where complexity dominates, and final answers where only evolving patterns are possible. This effort creates strain, not because it is wrong to plan or hope, but because it demands guarantees that reality does not offer. Chaos invites a gentler posture, one that allows plans to exist without demanding that they fully define what will come next. When the future is allowed to remain open, attention naturally returns to the present. Action becomes less about securing outcomes and more about responding with care to what is actually unfolding. Choices are no longer judged solely by what they produce, but by how they are made within uncertainty. The present moment becomes the primary site of meaning, not because it promises control, but because it is the only point where influence and awareness truly meet. This openness also reshapes how time itself is felt. The future no longer presses forward as a demand to be managed. It recedes into possibility, reducing the weight of anticipation and regret. The past settles into what has already unfolded, no longer competing with imagined alternatives. Between them, the present gains depth, experienced not as a bridge to certainty, but as a space of participation within a sensitive and lawful world. Letting the future remain open does not mean abandoning responsibility or intention. It means holding them without illusion. Actions still matter. Decisions still shape what follows. But they do so within a system that is larger, more interconnected, and more responsive than any individual perspective can fully grasp. Chaos does not erase agency. It places it within context, where influence exists without domination and meaning arises without guarantees. In the end, chaos offers not a warning, but an invitation to release the demand for complete foresight and to engage more fully with a world that unfolds through sensitivity rather than certainty. The future remains open, not because it is empty, but because it is alive, shaped continuously by countless small beginnings. And in allowing it to remain open, the mind itself can finally rest, no longer struggling to predict what comes next, but quietly present within the unfolding of what is.